has been known for 50 years, or that which hasn't is joint work with Greg Brumfiel. And it was our interest in these questions came from questions and discussions we had with Anton Kapustin when he was here, and it's closely related, at least as far as I can understand it, to work that he and Gaiotto did, or at least the mathematical part of the work that he and Gaiotto have done. They were interested in studying topological field theories, but in a context where you had fermions, and therefore the underlying manifolds on which the theories were going to exist are going to have to be spin manifolds.
Tend to be or
have to be? Well.
Okay. Well, I get
yeah. So they were interested in the spin version of cobordism. In particular, they wanted to know about what sort of action functionals they could have. So these would be homomorphisms from these spin Bordism groups to the circle. So that was the question. What I'm going to talk about, I'll give you a brief review of the spin groups, spin in, and spin structures. I'll talk about the low-dimensional examples. In fact, as far as I'm concerned, one of the hardest examples to understand is the one-dimensional example. It's quite twisted. And these examples are then closely related to one of my favorite algebraic objects, Orphan variance. And I'll talk about the relations. And then I'll do the two-dimensional case as a warm-up, and then the three-dimensional case, and questions about the four-dimensional case, where we have some ideas, but only conjectures at this point. Okay. Let me just remind you about the spin groups. So for every n at least 3, the orthogonal group SON, the special orthogonal group, has fundamental group Z mod 2. So there's a covering group, which is called spin n. This is the double, non-trivial double cover, the universal cover of SON. The inclusion of SON in SON plus 1 induces an isomorphism of fundamental groups, and therefore lifts to a nice commutative diagram of groups. And spin n is the pre-image in spin n plus 1 of the subgroup SON and SON plus 1. Now you can extend this series downward to SO2 and SO1. When you restrict the spin groups to SO2, you get spin 2, of course, double cover, and spin 1, which are a little bit exceptional. So, of course, SO2 is the circle. Spin 2 is also the circle, but the map is theta goes to 2 theta, or z goes to z squared. So this one's a little different in that its fundamental group is z instead of z2. This one is, spin 1 is the group of order 2, and SO1 is the trivial group, and again, this is t goes to t squared, the real square.
Spin 2 or SO2 on the street. Say I'm SO2 or I'm spin 2. You can't really show that. Well, I'm asking the question, is it an intrinsic property? You're supposed to say no.
No, I think what's intrinsic is this double cover.
Yeah, right.
Right.
But the other ones you can.
That's right. The other ones, because the fundamental group is Z2. Right. Okay. So those are the groups. Let me talk about spin structures on bundles. So suppose we have a vector bundle over space. This is an n-dimensional vector bundle, real vector bundle. it needs to be oriented, because we're talking about oriented things here. And let's impose a metric on the bundle. And in other words, we've reduced the structure group to SON. Okay. So we have, once we've done all of this, we have the SON frame bundle of E, the oriented frames on E. This is a principal bundle over the base, principal bundle for our structure group SON. And we say a spin structure on this bundle is a lifting of this SON bundle to a spin-in bundle. So a spin structure on E is a principal spin-in bundle. Let's call it P over X, and an isomorphism from P divided by plus minus 1, which is central inside the spin group, and therefore acts as an involution on the total space. What did I say? Frame SON of E. These bundles over X. So that's what a spin structure is. Now, when you have spin structures, you have associated Clifford algebra. Well, you always have the Clifford algebra bundle. But when you have a spin structure, you have the spinor bundle, and therefore its representations, and the Dirac operator, and all of that beautiful theory, which I'm not really going to talk about. Okay?
How do you see it on a vector bundle?
Well, I'm going to give you a couple of low-dimensional examples, 1 and 2. And we could also talk about 3. It's not so clear in general.
What?
It's not so clear in general. It's not a nice picture, but there's a beautiful picture in the low dimensions, which I want to talk about. Okay, so that's what it means for a vector bundle to have a spin structure. A manifold, a spin structure on a manifold well, first of all, it has to be oriented, and then it's a spin structure on the tangent bundle of the manifold. So you would have to impose a Riemannian metric on the manifold and then lift the frame bundle of the tangent bundle to a spin bundle. Okay. But in fact, that's the metric is really a red herring. The space of metrics is connected, and you can cover, if you have a spin structure with respect to one metric, as you vary the metric, you can vary the spin structure. So a spin structure with respect to one orthogonal metric determines a spin structure in every other metric. That's also true for the bundles. So we'll talk about an oriented manifold having a spin structure, simply meaning it's that equivalence class as you vary the metric. Okay. So the first question you would ask is, when do bundles or manifolds have spin structures, and how many do they have? These are well-known questions. They have well-known answers. So the obstruction to a bundle, or I'll just stick to manifolds now, to tangent bundles, to a manifold M having a spin structure is the second Steve Whitney class of the tangent bundle. This is a two-dimensional cohomology class with Z2 coefficients. If the manifold has a spin structure, it has to vanish.
You could say it's this element in the second cohomology class, which we'll call the second cohomology class. Otherwise, we'd left on one end.
Yes.
Like an extra thing to know.
Well, what I'm going to use about the Steve Whitney classes is I'm going to use the Whitney formula for them, which says if you have a sum of two bundles, E1 plus E2, the total Steve Whitney class, 1 plus W1 plus W2 and so on, is the total Steve Whitney class of the first times the total Steve Whitney class of the second. Right. So that's a property that these numbers have. All right. Well, once you have the existence question, there's the uniqueness question. And the number of spin structures of up to isomorphism if it has one, given one, the number is the cardinality of the first cohomology with Z2 coefficients. And in fact, the statement is much better than that. The set of isomorphism classes of spin structures, so isomorphism classes of spin structures on the manifold, is a torsor, let me use that word, for H1 of M with Z2 coefficients. In other words, this group acts on this set. If you have a spin structure and a cohomology class, you can act on the spin structure by the cohomology class, and you get a new spin structure. So this group acts on this set, and it acts simply transitively. So you pick one spin structure, you get a bijection between H1 with Z2 coefficients and the set of all spin structures. But that isomorphism depends on your initial choice. There isn't a canonical one.
It's like not affine space, but superfine.
That's right. Affine space, right.
It's an empty set if there are no spin structures.
Yes, that's right. Or empty. Okay. In fact, a spin structure is, well, in fact, an oriented structure is trivial over the one skeleton. Imagine the base is a simplicial complex. Maybe you have a smooth manifold and a smooth triangulation. If you restrict to the one skeleton, these bundles are all trivial, and the spin structure, if it exists, is determined by a class of trivialization over the one skeleton. And this action, the way it acts on the trivialization on the one skeleton, is just twists according to the cohomology class. So that's one way to think about these various classes of spin structures. They come from different trivializations over the one skeleton. And this is the obstruction to the bundle, at least in dimension 3 or higher, being trivial over the two skeleton. So a spin structure means the bundle is trivial over the two skeleton, and that's the existence, and the uniqueness is which trivialization do you have over the one skeleton. Okay? All right.
Orienting cover for this construction. The way to kill this.
Say again?
Is there an analog of the orienting bundle for the spin structures?
Orienting bundle. I see. You mean the top exterior power? No, I don't think so.
Oh, you said P divided by plus or minus 1 is the other thing. That's the double cover.
Yeah.
I mean, the closest thing that I know
No,
of is
but
that
isn't that-
if you
I'm
could
suggesting-
ask, if you take, is there a complex line bundle over the manifold so that the total space of the complex line bundle is spin? That happens sometimes. That's a spin C structure.
Yeah, that's a little different. Okay. No, I think he wants the analog of the determinant line bundle.
You can kill W1 by passing to a cover. Is the point. There was a double cover of a non-orientable manifold.
Is that what you're asking? Ah. No, because it's a two-dimensional question instead of a one-dimensional question. There is a Poznikov version of that. If you think of covers as fibers of maps to a k pi 1, there's a fiber of a map to a k pi 2 over which as a spin structure. But that would be the best you can do. All right. All right. So let's talk about spin structures on the circle. Well, the circle has a spin structure. W2 is trivial. Where did it go? There's no two-dimensional cohomology. And the circle has two spin structures. So let's find them. Okay. Well, the tangent bundle of the circle is trivial. If I orient the circle, put a metric on it, it's got more or less canonical, well, it has a canonical trivialization. So this is reflective of the fact that SO1 is the trivial group, and if you make a bundle with structure group the trivial group, that has to be the trivial bundle. But spin 1 is the square roots of 1. So I'm looking now for a bundle with structure group plus minus 1 whose square is this bundle. So I need a bundle with structure group plus minus 1 is simply a line bundle. Let S plus minus 1 act on the real line. So we need a line bundle over the circle and an isomorphism between the square of the line bundle and the tangent bundle, which we've trivialized. So it's a line bundle whose square is automatically trivial. Okay? Lambda is a real line bundle. Well, there are two of them, as we said there should be. We could have lambda trivial or lambda the Möbius band, total space of the Möbius band. Okay. Those are the two spin structures.
The isomorphism doesn't matter.
No. I mean, I want it to be, it has to be an SO1 isomorphism. So this bundle is naturally oriented. And if you impose a metric on, I mean, plus minus 1 gives you a metric. So this isomorphism is then unique. It reflects the fact that you have these groups. Okay. All right. So the circle has two spin structures.
Think of the lambda as coming as part of what its definition is that its square is identified with the tangent line.
All right.
So it's not just abstract line.
Yeah. I mean, the only choice here up to equivalence is the orientation. This one we've oriented because we've oriented the circle. This one's automatically oriented because the square of a real vector space has an orientation. Okay. Now, it turns out that one of these spin structures bounds a spin surface and the other one doesn't. And I want to try to sort that out. So let me talk in general, because I'll need in higher dimensions as well, about how you induce spin structures from a manifold to its boundary. So Wn plus 1 is a spin manifold, and its boundary is some n-dimensional manifold M. We look at the tangent bundle of W restricted to M. So here's W, here's M. The tangent bundle restricted to M has an extra direction that's not in the tangent space to M, and I'll choose the outward pointing normal. And I'll write the tangent bundle restricted to M as the outward pointing normal followed by the tangent bundle of M. That's my convention. This orients, if W is oriented, this gives an orientation to the boundary. If I were to choose the outward pointing normal last, that would give an orientation that differs by sign depending on the dimension. If I took the inward normal, that would flip the orientations over too. So there's a convention here. This is the convention we take. This is the analog of saying we embed SON, or this is saying we embed SON and SON plus 1 this way, rather than what would be my natural inclination to put it first. Put the A first and then the identity. Anyway, this is the way we do it. Once we've done that, not only do we induce orientations, we induce spin structures. Just because of my commutative diagram of groups, now W is spin. We have the frame bundle for W restricted to the boundary written as the frame bundle for the boundary cross R, cross over M, well, cross R, well, cross the trivial bundle. Okay, and now we have a spin structure here. Using my diagram of groups, which is now gone, you see that this induces a spin structure for M, well, compatible with the inclusion of the frame bundle here into the frame bundle there. Sorry?
You switched to the...
Yes, you're right. Thank you. Okay. So the boundary of a spin manifold is automatically itself a spin manifold with this convention. So the circle...
Wait, aren't you missing the statement that the spin structure near the boundary factors in this way?
No.
That's what I'm saying. What I'm saying is the SO bundle can be reduced to its structure group. The SO n plus 1 bundle can be reduced to the structure group of these.
Yes.
And therefore, this spin bundle, when you take you have a check cover where the gluing functions here in spin cover these.
Yeah.
And therefore, they're spin in
So that's all
near the
boundary.
boundary. Right.
At the boundary, actually.
But I would say,
Just need that the
wait,
orthogonal
let me
frames
to
of
the
the boundary
boundary,
stay
say
inside the
something
orthogonal
quiet.
frames.
Quiet. I mean, you could say you have a spin structure on the boundary, you can extend it in slightly by this convention, and you can say that that structure extends to the whole thing. You're saying if you have any structure, it induces one. I don't understand that. I mean, it's not what you need anyway. You need that in the statement I made. That the spin structure on the boundary extends a little bit by this stabilization, and then that should extend over the interior.
It doesn't in general, though.
No, but it does in general, but that's what you're asking.
No, he's saying that if you have a spin structure on the manifold with boundary, then it naturally induces
I don't see it.
Well, it's that the orthonormal frames on the boundary sit inside the orthonormal frame bundle of the manifold with boundary, as those special orthonormal frames where there's one element that points out. Now you take it, so you have if you have a double cover of the orthonormal frames, you look at the preimage of that in the double cover of the orthonormal frames of the manifold with boundary, and that gives you a double cover of the frame bundle of the boundary.
That's exactly right.
Yeah, but why is the spin structure that I have look like that in the boundary? That's what I'm asking.
Well, okay. So maybe you're asking if a check cocycle question. I have a bundle that has orthonormal overlaps. What does it mean to say near the boundary it looks like this? It means near the boundary I can restrict those orthonormal overlaps to a special set. And now you have to do a little check co-boundary argument to argue that in fact you can take the overlaps in the orthonormal bundle you started with here to look like that near the boundary. Okay. All right.
You can avoid it by just saying the structure on the boundary extends inside by producting, and then it has to extend.
But the way he defines spin structures, you don't need to do that. What you need is a double cover of the frame bundle, and that you have just by restriction. You don't have to extend.
No, there may not be that one.
Anyway, let's go on, gentlemen. Let's go on. So the circle is the boundary of the two-disk. The two-disk has a unique spin structure because it's simply connected. what is the induced spin structure on the boundary? Okay. Well, maybe I should take the tangent. Let's look at the tangent bundle. So with respect to the trivialization of the tangent bundle of the disk is simply to use parallel translation in 2 space. And with respect to that trivialization, we see the tangent to the circle making a rotation 1 as we go around once. Okay. Now we're passing to the spin structure, which is a double cover of the group. We're halving the angle. So as we take half the angle, the total winding of the tangent bundle to the circle as we go around is in fact pi, half of 2 pi. That means in the induced spin structure, the tangent bundle of the circle is a non-trivial bundle. So in fact, the boundary of D2, the spin boundary of D2, is lambda non-trivial over S1. Sorry? It's called Nerver-Schwarz? Okay. I mean, if you're familiar with the Dirac operator, you know this. Dirac operator for the non-trivial bundle has no 0 modes. It's an isomorphism. The Dirac operator for the trivial bundle has a kernel and no co-kernel. It has index, which is well-defined mod 2 to be 1. So there's another way to think about this. On a surface, the structure group is SO2, which is U1. So the tangent bundle of the surface is a complex line bundle. In fact, much more is true because there's no integrability question here. The orthogonal, choosing an orthogonal structure gives you a complex structure. So the tangent bundle is a nice holomorphic complex line bundle. And a spin structure is a square root of the tangent bundle. It's thought of as a complex bundle. So it's a complex line bundle and an isomorphism of the square of that complex line bundle to the tangent bundle. Sometimes you write it as. And there are, of course, 2 to the 2g of them. These are the theta characteristics for Riemann surfaces. And our picture for the disk is this non-trivial line bundle over this the disk restricted to a neighborhood of the circle. We have this non-trivial line bundle, this Mobius bundle. Tensor over RC is isomorphic to S1 cross C. So if you think of this, this is a trivial complex line bundle over the circle, and this real bundle inside it is a twisting Mobius band. And then you trivialize the complex bundle. So that the real one winds around a half integer. Now we square it, and we get, again, the trivial complex bundle. Now this sub-real bundle is twisting an odd number of times mod 2 because we squared, and that's our fact that the tangent bundle twisted 1 with respect to the trivialization. So you can, in this case, think about spin structures by calculating winding numbers in the tangent bundle mod 2 rather than having to worry about Mobius bands versus trivial bundles. Okay. All right. So it turns out that I guess I've already said this, the spin Bordism in dimension 1, I guess it's time to introduce that. I'll write it this way. Spin Bordism in dimension 1 is a group, cyclic group of order 2, and the circle with the trivial spin structure is the generator. All right, so let me just say what all these words mean. The spin Bordism in dimension n, it this way, is generated by closed spin N manifolds. The addition, this is an abelian group, is disjoint union. And we have an equivalence relation. We say that a spin manifold is equivalent to 0 if it's the boundary of an n plus 1 dimensional spin manifold. Okay. So in dimension 1, we have every manifold is going to be a disjoint union of circles. The circle has two spin structures. One of them bounds, the other one doesn't. If you take two copies of the non-bounding spin structure, there's a little pair of pants. Cobordism.
Say a spin in manifold here is a spin manifold with a fixed spin structure. It's not just one with W equals 0.
That's right. When I say a spin manifold, I have chosen a spin structure. Right. If you take non-trivial spin structure and you do this operation, this is a nice spin manifold, and what you'll get at the other end is a trivial spin structure that is, say, the non-trivial bundle. So this spin group in dimension 1 is a cyclic group of order 2. Let's look at the spin group in dimension 2. Spin Bordism group in dimension.
Very quickly, that this is detected by an index. I don't know if you need that in higher dimension.
No, I won't. I'm not going to mention the Dirac operator again. So what about two-dimensional spin Bordism? Now, this is very interesting. And we get to the Orphan variant. So if I have a compact Riemann surface, with a spin structure, so it's a spin surface, I'm going to define a quadratic form on the first cohomology with Z2 coefficients, values in plus minus 1, quadratic form. It's quadratic over the cup product or intersection form in the sense that q of x plus y is q of x plus q of y plus, well, maybe I'll write it this way, the integral of x cup y over sigma. Okay? So it's quadratic in that sense, and also q of 0 is 0. Right? And it goes like this. Here's your Riemann surface with spin structure. Let's take a loop. So every element in the first cohomology is Poincare dual to some loop on the surface. And I want to define the value of the quadratic form on that loop. So the loop is gamma. So I take the tangent bundle of the surface, I restrict it. So gamma, I've written it as an embedded loop, but just think of it as a map of a loop to the surface. Take the tangent bundle of the surface and pull it back to gamma. This is a two-plane bundle. And I don't want to say this. It has a spin structure. I want that spin structure to be written as the non-trivial line bundle over gamma tensor over RC. So this is the non-trivial bundle representing the trivial spin structure. So I can also think of this as lambda plus over R lambda. When I take the square, this gives me the tangent bundle plus the normal bundle. So I have an isomorphism between the pullback of the tangent bundle of sigma as the tangent bundle of gamma plus a bundle that I'll call the normal bundle. Immersion theory tells you this produces an immersion of gamma in sigma, well defined up to regular homotopy. So in fact, this curve by this construction is immersed somehow in the surface, and Q of the class dual to gamma is simply the number of double points of this immersion. If you think about what happens For a trivial gamma, you're talking about, say, gamma mapping into a disk. And we get 0 self-intersection because this is the picture. There, the restriction of the tangent bundle of the spin structure is the non-trivial spin structure, non-trivial bundle over the circle tensor with C. So that's where this equation comes from. This is a nice geometric exercise. So we have a quadratic form, quadratic function. It has an Orphan variant, which is in plus minus 1. And it's simply 1 over the square root of the order of the group, some 2 group, times the sum of minus 1, the q of x, x in the first cohomology.
If you take the induced spin structure on an embedded circle representing the class, whether that's the induced is the interesting spin is the Möbius band or the trivial one?
No, it's always trivial. I mean, everything is oriented, so the bundles are always trivial. It's a question about the spin structure. So embed it.
I'm just saying, but if you take the induced spin bundle on that circle, whether it's the Möbius band spin structure or the one where corresponding to the trivial bundle, but then you find it one of them.
Let me say it this way. So the spin structure determines a trivialization of the bundle, the tangent bundle over the circle. We have an embedded circle. Its tangent bundle or normal tangent line or normal line will rotate a certain amount as you go around the circle. If it rotates an odd number, you get 0. If it rotates an even number, you get 1. Right. It rotates an odd number, you get 0. It's because we're now implicitly taking the parallel spin structure on the circle, which is the non-trivial spin structure. So it's the opposite of what I've said here. But yes, you can do it simply in terms of embedding it, restricting the trivialization coming from the spin structure, and counting winding numbers. Yeah. Anyway, let me do a simple example. If I think about H1 of the 2 torus with Z2 coefficients, it's a group of order 4, and its Z2 intersection looks like that, with, say, bases A and B. So we have Q of A could either be plus or minus 1. Q of B, well, let's take the 2 cases. Q of A is plus 1. Let's say Q of B is plus 1. Then Q of A plus B is also plus 1. And Q of 0 is minus 1. Minus 1, minus 1, minus 1. Q of 0 is plus 1. So in that case, we'd get 1 vote out here at plus 1 and 3 votes at minus 1 for a total of minus 2. Sorry?
Mod 2, so that plus and minus 1.
Yeah.
You're saying the multiplicative group.
Yeah, so plus minus 1.
So 1 is 0 and minus 1.
Right. So this is the trivial element. So I have 1 vote here at plus 1, 3 votes here at minus 1. They add up to minus 2. I divide by the square root of 4, which is 2, and I get minus 1. Now, any quadratic form on a Z2 vector space of this type is a sum of these, and you see this thing is easily that this thing is additive. The other possibility is either Q of A or Q of B. Sorry. If Q of 2 of them is 0, Q of the third one is 1, and Q of 0 is 1, and you get the opposite picture. Anyway, it's a nice little exercise about Orphan variance. It's easy to see that I gave you a geometric description of the invariant. It's easy to see it's independent of the homotopy class or even the homology class. It only depends on the homology class of the curve. It's also not hard to see that if the spin surface is a spin boundary, then on the image of H1 of the 3 manifold that it bounds into H1 of sigma, take the image of this. This is a subgroup of the square root of the order, and in fact, it's a self-annihilating subgroup, so the form breaks up this way. It's a Lagrangian subspace. And furthermore, an immersion version of the argument that shows this intersection is 0 shows that Q restricted here is identically 0. And thus, this thing breaks up into trivial pieces. Some ends like this, where Q of one of the variables is 0, so you never get this case. And that implies the Orphan variant is 0. So the Orphan variant is a well-defined function from the two-dimensional spin Bordism to Z2. And it's not too hard to prove. It's an isomorphism. Milner's not in the audience, right? So in dimension 2, spin structures and what are called stable framings are the same thing. And Pontryagin had the idea around 1950 that one could compute homotopy groups of spheres using stable framings. And he computed pi2 to be trivial because every surface bounds a 3 manifold. He forgot about, or he didn't realize it was an Orphan variant. So the stable 2 stem is Z2, and this is it. And as Milner said, Ellis Pontryagin made a mistake, and Ellis Pontryagin is no fool. A very subtle invariant. Okay. Before I get to dimension 3, I have to talk about one of my favorite subjects in dimension 2, Pinminus manifolds. I tried to convince Tony to come, but I see I didn't succeed. So Pinminus manifolds. So here we're taking the analog of spin manifolds, we're allowing them to be non-orientable. Turns out there are 2 kinds of non-orientable covers. I won't go into why. It's sort of pretty clear if you think about the group theory. This is the one that has the following description. An N manifold has a Pinminus structure if the tangent bundle, I could do this for bundles, but let me just do it for manifolds. If the tangent bundle plus a line bundle has a spin, is given a spin structure. So a pin structure on a manifold is a spin structure on the manifold plus a line bundle. Well, let's just think about our Steve Whitney classes. What is W2 of the sum of this? Well, it's W2 of the tangent bundle plus W1 of the tangent bundle times W1 of lambda 1. And W1 of the tangent bundle is W1 of the tangent bundle plus the line bundle is W1 of M plus W1 of lambda. Well, spin structure says this is 0 and this is 0. So we see that lambda is, in fact, the determinant line bundle of M. And this tells us W2 of M plus W1 squared of M equals 0. So this is the obstruction. Okay? For pin plus, the obstruction is W2 equals 0. Okay? All right. Well, we have a version of immersion theory for surfaces. A spin bundle over a 3-dimensional spin bundle over a Riemann surface is trivial. And it has a unique trivialization up to equivalence. So in fact, for surfaces, we can say the tangent bundle of the surface plus a line bundle, the determinant line bundle, is trivialized. Well, this determines an immersion of the Riemann surface into 3 space, because this is the tangent tangent bundle, the 3 space restricted to the surface. So we have an immersion up to regular homotopy. That group was calculated, I believe, by a student of Milner's named Wells. Is that right? Bob Wells calculated this group. It's the cobordism of immersions is a cyclic group of order 8. Later, Ed Brown defined an Orphan variant, which I'm going to tell you about. Not this one, not the one I was talking about before, a slightly more subtle Orphan variant, and which takes values in Z mod 8, and he showed how to associate to a picture like this a quadratic form, and therefore an Orphan variant, and this gives the isomorphism between spin cobordism and Z mod 8. In fact, were you the one who pointed out that? Maybe Ed did. Certainly he gave the definition. I mean, he gave this example, but I don't know the history of who knew what first. Anyway, the Orphan variant I'm about to tell you about produces for a Pinminus structure or on a surface or a surface immersed in 3 space, produces a quadratic form that has a Z8 Orphan variant, and that's the isomorphism between this Bordism group and Z mod 8.
I thought it was called Brown invariant.
That Orphan variant was defined by Brown. I would refer to it as Brown's Orphan variant.
I think Tony Phillips made the pictures of the immersed Bordisms and so on, showed how it was the 8.
Yeah, he took the boy's surface, and I think, and took 8 times it, and a movie of how 8 times it, or 8 copies of it.
Down here, and I told them that they had an algebraic Z8 up there at Brandeis, probably the same thing.
Yeah.
Someone who made the connection.
Yeah.
I mean, you can make the connection, right? You see what the quadratic form was from Tony's pictures. Just look at a curve to see whether it's moidus strip or twisted strip.
Okay, that's where we're going. So the kind of quadratic form I'm going to consider now will be, again, on the first cohomology with Z2 coefficients, but instead of taking values in plus minus 1, it's going to take values in a group I choose to write this way. It's a cyclic group of order 4, half integers over even integers. And the reason I write it this way is so the quadratic condition is still the same. So this is an element in the integers mod 2, which is naturally a subgroup inside here. And this is the quadratic condition, and Q of 0 is 0. These quadratic forms, when you take a quadratic form like this, and you define its Orphan variant to be, well, it's the same formula, really. 1 over the square root of the order of the group. Replace minus 1 by e pi I q of x, sum over x in the group. Okay. And this turns out to be an 8th root of unity.
Like another theorem, right?
Yeah. Well, I mean, you can prove it directly. Yeah, because you can classify everything. Let me do a simple case. Suppose we have x dot x. We have a one-dimensional space. Since the intersection form is non-degenerate on a one-dimensional space, x dot x x's generator has to be 1 mod 2. Okay? So q of x plus x, well, that's q of 0, so that has to be 0. It's got to be q of x plus q of x plus x dot x. This is 1, so this has to be 1. So q of x is either plus or minus a half. Okay. So let's do those two cases. So suppose we do plus a half. That'd be there. Q equals 1/2. Q of 0 is 1. And the sum of these two is the square root of 2 times e to the 2 pi I over 8, the standard generating eighth root of unity. If I do the other example, where Q is minus a half, I get this one, the negative generator. And those are, when I divide by square root of 2, I get the eighth root of unity in both cases, and eighth root of unity. All right. Now I want to talk about 2- and 3-dimensional spin Bordism and try to calculate the dual group. So I want to try to calculate the homomorphisms from spin 2. Actually, I'm going to do what's called reduced spin of x into R mod z. And hom of, well, it doesn't matter in dimension 3, spin 3 of x into the circle. And try to give explicit representatives for these groups and say how they evaluate in some geometric or topological sense on a spin Bordism element. That was Anton's original question.
So what does it mean to these groups?
Sorry?
What do these groups mean? You have an example?
Yeah, so I'm going to tell you. Yeah, so this is a generalization of the abstract spin Bordism groups we've been talking about, where you consider maps of the spin manifold into X. So these groups, spin n of X. X is a topological space. These are generated by closed spin manifolds and continuous maps into X. Those are the generators. It's going to be an abelian group. Addition is disjoint union of manifolds and maps. Of course, the maps might have images that hit, but that's not relevant. Okay. And as an equivalence relation, we set M and F, a representative, equal to 0 if it's the boundary. There exists a W n plus 1 spin and an F into X, such that the boundary of WF in the spin sense is MF.
So if X is a point, you just get ordinary space.
That's right. Special case of a point gives you the groups I defined before. Maps are irrelevant. So these turn out to be finite, well, for a reasonable X, these turn out to be finitely generated abelian groups, and we're interested in the character groups, the Pontryagin dual groups, and explicit representatives. So I was hoping to tell you about the Atiyah-Hirzebruch spectral sequence and how we actually think about these spin groups, but I see I don't have time, so I'll just tell you the answers. The two-dimensional answer is quite simple and I think has been known a long time. So suppose you have a surface mapping into a topological space. You have one obvious invariant is the image of its fundamental class in the second homology of X with integer coefficients. And a second invariant is associates to each Z2 cohomology class in X a spin manifold T in sigma. So this is a spin 1 manifold in sigma.
What's the index of that class?
A compose F.
That's a 1, H up to 1.
T.
A is where?
A is in H upper 1. One-dimensional cohomology class. So if you have a one-dimensional cohomology class, you can think of that as a map to RP infinity, or let's say RP large N. You can take the pre-image under this composition of a codimension 1 submanifold in there, assume the map is transverse to it, and you'll get a 1 manifold in sigma. It's because everything's oriented, its normal bundle is trivial, and therefore T inherits a spin structure. So we can say the spin class of ft of f composed with A is in this one-dimensional spin Bordism of a point, which is Z mod 2. So I now have two invariants associated to this. Well,
Instead of taking a line bundle on X, a real line bundle, pull it back, make a generic section through it, then.
Yeah.
so let's start with a two-dimensional cohomology class on X with R mod Z coefficients, and a one-dimensional cohomology class in X with Z2 coefficients, P and A. And let's evaluate P and A on a spin surface to give the integral over the fundamental class of sigma of P, that's an element in R mod Z, plus 1/2 the spin structure of T of F compose A. So this is an element in R mod Z. This is a half integer mod integer, so it's also in R mod Z. This determines a bijection between H2 of X R mod Z cross H1 of X Z mod 2 and homomorphisms of spin 2 reduced of X into R mod Z. So this construction is clearly additive in this variable because addition here is disjoint union, and therefore the integrals add and the spin structures add. So this evaluation does produce a homomorphism associated with every P and A. Standard arguments, the Hertzsprung spectral sequence, show you that if P and A vanish on a spin Bordism element, it can be deformed to a point, and therefore it's a reduced element. Therefore, in reduced theory, it's trivial. So that shows you that this function, that shows you something, that if an element in spin Bordism is killed by all these elements under the homomorphisms, then it's 0, and it's not too hard to prove it's in fact a bijection. But it's not a group isomorphism because it's not a homomorphism. The group structure over here has to be given this way. Now, it's an abelian group structure, but it's a non-trivial extension. Anyway. And then with this group structure, this is an isomorphism. Okay. So let me say what happens in dimension 3. In dimension 3, you would expect, analogous to what we had here, 3 classes. You would expect a 3-dimensional cochain, a 2-dimensional cocycle, and a 1-dimensional cocycle. So I'm using a shorthand now. These represent cocycles. These are cochains. I haven't said the space, but there's some underlying space here. They satisfy a relation. I should say this is with R mod Z coefficients, and these are with Z mod 2 coefficients. There's a relation between W and P given by this equation, and you divide out by fairly obvious boundaries, namely d xy dz plus 1/2 t dt dt dx. So x would be a 0 cochain, t would be a 1 cochain, and z would be a 2 cochain with R mod Z coefficients. The group structure in this case, analogous. Yeah, means the third cochains on X with R mod Z coefficients. The second cocycles was Z mod 2, and the first cocycles was Z mod 2. Yeah, this is Z mod 2. And there's an implicit X here. The group multiplication is sort of interesting. Let me just write it down to indicate to you we had to do some work. where alpha p a.
Half. Middle.
Sorry?
1/2 AB in the middle.
Yes. No, I shouldn't. No. No, the 1/2 is somehow here. Okay, this is 1/2 p cup 1 q plus p plus q cup 1 ab plus a cup 1 b plus 1/4 capital A capital B squared. These cup 1s are the higher cups of Steenrod operations. Capital A and B, little a and b are Z2 cocycles. Capital A and B are integral lifts of those cocycles. They're not cocycles. They're defined to be the unique lifts that take values 0 and 1 only on the generating one-dimensional simplices. So these are canonical lifts. So that's what you have to add in here. And notice there's some sort of 4 extension. So that's the group law. With these relations, you get a group G of X, and this group is isomorphic to the dual of spin 3 Bordism. And let me just briefly tell you how the evaluation goes. If you have a spin 3 manifold mapping into X, you have a one-dimensional cohomology class into RPN. The pre-image here now is a sigma, a surface, and it's a Pinminus surface. So it has a Z8 Orphan variant. So these elements of order 2 here in the cocycle law, in fact, produce homomorphisms of order 8. So that shows you the group has to be fairly non-trivial. As far as the P goes, suppose the P is actually induced from a map to the 2-sphere. So phi star of some generator on the 2-sphere is P. Then the value of P is 1/2 the spin structure of phi inverse of a point. You get an element of order 2, you get a one manifold back in X with a trivial normal bundle, so it has a spin structure, and you take 1/2 that spin structure. And W, of course, you simply integrate W over F star. Yeah. So it's an analogous to what happens in dimension 2, but quite a bit more complicated. And I'd love to do dimension 4. I think I know what the formulas are, but makes this look like a piece of cake. They're long, involving cup 2s and cup 3s, and it gets complicated. It's the same set of groups. There's not another homotopy group to add. So it should be a 4 cochain, a 3 cocycle, and a 2 cocycle. But the group law is more complicated. The evaluation is going to be quite a bit more complicated. But I think an analogy of this works in dimension 4. And with that, I'll stop. Thanks.
You have 1/2 AB there. A and B are 2 mod 2 classes. You're multiplying them and then dividing by 2. Doesn't sound kosher. So can you explain why
Yeah.
that makes sense?
So I'm thinking about Z mod 2, I think I'll write that way. If I take a 1/2, I end up in a 1/2 of Z mod Z.
Well,
Which
don't
is
have such a map. 2 maps.
Sorry? I mean, these are free abelian groups, so there's no
1/2 Z mod Z.
there's no issue about what half of this thing means. And if I vary it by an even integer, by the time I multiply by 1/2, I'll vary it by an ordinary integer.
That's still Z mod 2 there.
Yeah, these groups are isomorphic to Z mod 2, and this is an isomorphism. I've just chosen to write it in a different way so that this embeds in R mod Z in the obvious way.
Think of Z2 that way, then A times B is.
Yeah, you have to think of A times B in here. Right. and then take a half. You don't take a half of A, a half of B, and then multiply them. That wouldn't work.
You 0, 1, you have it, you get 0 and a half.
Right.
Shift by nothing or shift by
Well, A is a mod2 class. You say there's an operation,
That's right.
which is cup product times a half. So
Right. So you can go from H1 of whatever my space is, tensor H1, whatever my space is, into H2 with R mod Z coefficients.
oh, R mod Z coefficients.
Yeah, this is P's in R mod Z. Yeah, I'm not going back to the Z2 coefficients. Right. And it's cup product ends here, and then you just do this shift.
Potential math comment?
Yes.
I mean, so this is getting like so complicated it's even beyond John Morgan's comfort zone, right? So, but there are abelian groups.
Yes.
So you have this sort of complicated way of presenting abelian groups. And they look like group laws, right?
Yes.
Now, I once tried to learn about finite characteristic up in and then Barry Mader said it all happens with abelian group laws. So there's a theory of abelian group laws and finite characteristic, which is quite elaborate. So I'm wondering if you would just put this in the context, in that context, maybe the natural examples there would appear. Sort of like Jack Morava country, you know, the rod algebras, automorphisms of the fundamental abelian group law on the line, stuff like that. So there's a lot of smells of that theory standing around.
I mean,
it should be natural, you know. I mean, you're finding it.
So it is we're really talking about a three-stage Posnichoff tower. So if you have a one-stage Posnichoff tower, what are maps into it? They're represented by cocycles mod coboundaries. If you have a two-stage Posnichoff tower, how do you think about that? You have a cocycle, and then you have a cohomology operation, and you have to have a cochain that kills that.
And these group laws have ice also.
Right, so this is the next stage. So, in fact, maybe there is a description like that. It would be nice to see it. Yeah, call it Morava. But yeah, when you think of it that way, it just gets more complicated than you can keep track of. And this, in some sense, is figuring out what that three-stage how that three-stage Posnichoff tower can be described.
And they need it for physics. So what's the physics? What are the words?
Well, I said as much as I know in the beginning, which is you want a topological field theory, but it's supposed to have fermions in it, so you're going to have to put it on a spin manifold. So it's, the Atiyah-Siegel axioms. You want something that associates to spin manifolds, numbers, and it's an invariant, or, well, this is going to be numbers, I guess, and it should be invariant, should be 0 on spin boundaries. Maybe that's the action rather than the partition function, I'm not sure.
So in your abstract, you said more.
I did? I take it back. Well, Anton, I think, is interested in thinking about topological insulators. Yeah.
Okay.
Right, topological states of matter with fermions. But I couldn't read his paper, so I don't really know what he did. Right, the question was precise, and in fact, he was, he had many of these. He certainly knew the Riemann surface case, and he was sort of struggling toward the three-dimensional case. I don't know how much he figured out, but I couldn't sort out what he had done. But they wanted it in terms of a triangulation, and you put fermions on opposite sides of edges. Those are somehow your fundamental discrete things that you're going to do some partition function with, sum up over. And he wants a three-dimensional.
Can you convert it to his language?
I don't know. And I don't know. I mean, the hope was if you get it geometric enough, it will convert.
I mean, that's very weird, too, that capital A, capital B, right? That's very weird.
Yeah. That actually simplified. He had a much more complicated version. So his relation, Anton. So he started off with the relation dW is 1/2 or plus 1/2 p squared plus 1/4 the Pontryagin square of a squared. But this class capital A is a way to kill this thing. A to the fourth kills this. Or dA cubed, I guess, kills this. Right, Pontryagin. Right, same Pontryagin. This is the E4 cohomology class. And then the formulas, so we were originally working here, and the formulas are even longer, but this capital A, which seems unnatural from some points of view, simplifies things quite a bit. All right.